Great. I think we have a good number of people, so I think we'll kick things off. So, hi everyone, and welcome to today's webinar. I'm Tom O'Doherty, the Acting Head of Innovation, while Kate Fazio is away on parental leave. I want to begin by acknowledging the traditional owners of the land and pay my respects to their elders, past and present. So we have a very exciting webinar for you today, just to update you on the progress over the last year, I suppose, of the AI project. What we've been developing and where we've got to so far. I think it's probably a good opportunity as well to thank everyone for their participation, especially around the tagging game. I think it's been really important work there, good involvement and participation to get those tags so we can train the model as well. Today we'll be hearing from a number of people. First will be Braden Merrifield, who is the project lead and main developer for the AI project at Justice Connect. He actively works with the technologies and has been very involved across the board with everything we do, including the pro bono portal. We'll hear from Tim Baldwin, who is Melbourne Laureate Professor at the School of Computing and Information Systems at Melbourne University, and Director at the ARC Training Centre in Cognitive Computing for Medical Technologies. And Mel Mistica, who's a research fellow with focus on natural language processing. So they're the people who will be presenting today, and Braden will be taking you through the presentation. So probably a good point for me to hand over to Braden.
Thanks, Tom.
Yes.
Hi all, my name's Braden. I'm the developer and project lead for the AI project at Justice Connect. I've been with Justice Connect for 2 years and have a background in software development. I want to start by thanking everyone in attendance today. We've been hard at work on this project for near on 18 months now, and a lot of the work that we've done wouldn't have been possible without a lot of your help here. So it's very much appreciated. Today I'll be touching on AI in the legal sector to give you a better idea of where attention is being focused within the sector. I'll also be covering Justice Connect's application of artificial intelligence, why we've decided to go with an AI solution, and what the process of building a classifier looks like. Following this, I'll touch briefly on results before passing over to Mel and Tim to talk more deeply to the nature of classification and a bias in artificial intelligence, as well as some of those results. So what does AI in the legal sector look like? Recently, the legal sector has put a lot of focus on e-discovery and contract work. So for those of you who aren't familiar with e-discovery, this is the collation and identification of documents often requested by a judge for use in a lawsuit or a case. The use of this AI applications for this technology is often quite obvious. A lot of work goes into collecting these documents. It's really tedious and cumbersome work. So these tasks can often take many hours and time to complete without assistance. The main benefits being that they save time and allow individuals involved in this work to do more fulfilling work. At the forefront of AI is litigation prediction, and this is technology that really aims to help a lawyer get a better sense of how long a case might take to settle, and whether a case will be successful given a history of a judge. With this particular application, there's been a lot of issues around using older data, being that it tends to be a bit more biased and with an older way of thinking. So it has run into some issues in that sense. So yeah, applications for artificial intelligence. Applications for artificial intelligence, as you've just seen, a lot of the time are based on text. Those previous applications have a really common theme, which is that they're all highly dependent on text and entail large amounts of data. Underlying to all of these applications is what's referred to as a text classifier. And to put this simply, it's an algorithm that takes labeled data and provides a weighting for some given context. A really outlandish and probably simple example is, say you had a chef who authors recipe books, and he doesn't like to use the word onion and instead replaces it with a phrase like the thing that makes me cry. So if you were to go through this book and label all of these phrases as being onion related, the classifier would learn that these things are specifically onion related. And if you were to feed another book from that author into this classifier, that classifier would be able to tell you with some degree of confidence what pieces of text are specifically onion related. So that's a really simple example. And in the real world, use cases are often have a lot more subjectivity and they're a lot more complex. And with that comes the need for a lot of data. There's obviously nuances with figuring out these more subjective problems. And so just like you would when learning yourself, you need more data to figure out something that's more complex. You need to have a better understanding. And so at Justice Connect, we've identified a problem that we think is solvable with data, and we just happen to have a process of data procurement that gives us the means to solve this problem. So that problem is relating to our online intake. And so part of what Justice Connect does is we assist people through varying programs. These programs relate to different contexts that the people may have a problem with. So as part of the intake process, a help seeker comes through, they describe their problem, and that may be through text or through other means, whether that's through checkboxes or describing their means through other drop downs, but also through text. Oftentimes, what we've found is users can't identify their area of law. They struggle to identify exactly what their problem is. Even with assistance from the types of questions we're asking, it still isn't clear to them exactly what their problem is. And what this leads to is a triage process that is a lot more cumbersome and requires a lot more work to get that person help. Using the data that these individuals provide, we soon come to realize that we can assist them with an AI solution by using the information that they provide to give them a suggestion as to what exactly their problem is. You might be wondering, what's the purpose of this? I did just explain that triage is an important part of this. There's many factors really as to why AI is the solution here. Natural language varies significantly, and you'll often find that the way one person describes their problem compared to the way another person describes their problem is completely unconnected, besides some keywords. So, and this applies to several cohorts, whether somebody is senior or whether somebody is homeless or somebody is of almost any background. It can really affect how that person describes their problem. So why are we doing it? The main benefit here is that by us providing a suggestion using the data that the help seeker gives us, when I say us providing a suggestion, that is the classifier or the artificial intelligence reading in and coming back with a calculated conclusion as to what the problem may be. By us providing this solution, it enables the user to get help quicker. It also means that our triage process is smoother. We can get people in the door and get them to the right place and get them help a lot quicker. It also means that our staff members spend less time doing triage work, which might not be as engaging as they'd like, as fulfilling as they'd like. It gives them capacity to do other tasks. And we all know within the not-for-profit world, time is money, and it can be quite difficult to allocate time effectively, especially when you want to help as many people as you can. So there's numerous benefits as to why we might want to employ AI as a solution, and quite evidently we had looked at other solutions that might work here, but AI was really the only pathway. You can't really write code to handle all of the cases of natural language. It's just not feasible. So I want to talk to what it looks like to build a classifier. I want to cover this process in a bit more detail from a project perspective. There's really 4 key components, and that is data procurement, which is the data collection, establishing a data schema via data analysis, and then early data assessment and model training. So this project kicked off back in 2019. We were able to join with Melbourne University. Without their expert knowledge in the field, we wouldn't have been able to do this project. They have a really strong background in language and AI. And they really bring the ability for us to be able to use or create a model through artificial intelligence algorithms. So from the get-go, our focus was really understanding the data we have. In order to analyze the data, there was a process of back and forth for establishing what fields we need to know to analyze and assess the classifier's outcome. And then what we need to label in order for the classifier to function as expected. This was really the initial work we did. Once we're able to define these parameters, we could pivot our attention to creating a game, which is TAG, that would enable lawyers to label our data according to an area of law set. Many of you will have participated in TAG. It's been really the core tool for us to enable lawyers to do a lot of the heavy lifting for us, which is that labeling work, to collect that vital data to enable our classifier to be able to classify the kinds of problems that people are having. So using TAG would allow us to better understand the type of data we're working with. Some of you might remember the email that I sent out some time ago, which entailed Krippendorf's alpha, and all that really was a measurement of agreement across lawyers for different areas of law and on particular pieces of text. So that was, whether if you had put something as being a banking and finance related issue, whether there was agreement between lawyers as to whether that particular thing was exactly a banking and finance issue. So we do analysis in that sense to understand whether our areas of law are acting sufficiently and to define to help us to better define those legal areas within the data if need be. So making use of that labeled data, we were able to generate a preliminary model. So that preliminary model has performed really well across several areas of law, and for the most part met our early expectations. It has fallen short on particular demographics, and we do have some thoughts as to why that might be the case. But this is a process of further training and iteration. So what we don't catch this time will allow what we don't catch this time, we will be able to catch next time, because we do that analysis and can figure out, okay, we don't have enough data on these particular areas of law. Let's go out and collect that data, or these particular cohorts are struggling. Let's collect data from those particular groups and make sure that the model is trained on that additional data to smooth out those gaps. So I'm going to pass over to Mel now to talk a bit more closer to classifiers and the model more generally, more specifically. Pass over to you, Mel.
Thanks very much, Braden. Okay, let's see. Sorry, let me view. Okay, thanks very much for priming them for me, Braden. Okay, so thanks very much. This is the Melbourne Uni team. First of all, I'll be talking to you in a bit more detail about the classifier, what Braden started to talk to you about. And then, so basically I'll be talking about what we did with your annotations and how we built the classifier. And then Tim is going to talk to you about the next steps based on what we had learned in the last year and the results that we got from the classifier. And Jehan is also here, and the three of us will be here at the end to answer any questions that you have. Okay, so building a legal classifier. So I think Braden talked to you a little bit about why we need a legal classifier. So our primary task is really to help these poor triaging lawyers. We don't want them stuck under piles and piles and piles of text. And so what we built was what we wanted to build was a legal classifier that would help pre-sort these requests that were coming in to see whether the requests were coming in actually required legal help, and if they did require legal help, which area of law did they should they be categorized under. Okay, so how did we build this legal classifier? So as Braden said, we built this classifier from your annotations or the legal expertise that and your experience that you encoded via the tag game. And what we did with your annotations was that we created a data set, what we call a gold standard data set. It's a definitive data set that the model can learn from. And this is how we guide the model or the classifier that we're building. Okay, so just to give you a bit of some examples of what you guys had annotated. So in the first line, we had this short document: roommates are refusing to pay bond money. And for this particular text, for this document, we had 7 lawyers annotate this document. And you can see that all 7 of them agreed that it should be categorized as housing and residential tenancies. And then there was one who thought maybe it was property law or thought it was property law, and another one who thought it was litigation and dispute resolution. But they all agreed that it was definitely housing and residential tenancies. However, in the second line, you see here that there were 5 annotators, and all 5 of them seem to have had different ideas about what this text should be classified as. Sorry, Jehan just entered. So here you see that a majority of them thought that it was that this bit of text should be labeled as corporate and commercial law. 3 of them thought it should be public and administrative law. So in situations like this, where you don't have, unanimous agreement, what do we do? So we have to try to create a data set where we say, well, we know definitively for this text, it's definitely these areas of law. So then we could feed it into the model and the model can learn from that. So what happens? How do we build this data set when there's no unanimous agreement? So how do we create this data set from your tag game annotations? So just to give you another example here, we had for this document, we had 3 annotators, and the first annotator thought that this text should be labeled under employees and volunteers, and they were 100% sure that it should be. That's what the 1.00 is. That's what that stands for. It's 1 out of 1. And they also thought that the first annotator thought that it should be labelled as litigation and dispute resolution, but they weren't quite as certain given the text that they had in front of them. The second annotator was 100% sure that it should be labeled employees and volunteers, as well as litigation and dispute resolution. And the third one was, kind of sure, pretty sure that it should be personal safety and employees and volunteers. So of all of these areas of law, personal safety got 1 vote, employees and volunteers got 3 votes, and litigation and dispute resolution got 2 votes. And the way that we decided the way that we decided how these texts should be annotated by looking at the number of votes and seeing, looking at the majority. I'll start again. I'm so sorry. I'm a little bit nervous here. So what we did was we decided that we would look at the majority vote to determine what areas of law applied for each particular text. Okay, so for that particular text, given that employees and volunteers got over a majority of the votes, that is, it got 3 out of 3 votes, then we applied that label to that piece for that text. And for litigation and dispute resolution, that got 2 votes. For litigation and dispute resolution, that got 3 votes. We also applied that label to that text. And so that became part of our gold standard data set. Okay, so I want to break down what our data set looked like. And if you have a look at all of the documents or all the instances per area of law, you see there aren't actually a huge number of instances under each of these labels. And so actually, usually when we build models for AI or for NLP, normally we have, often we have tens of thousands of instances. And in this case, we had a total of around about 4,000 documents. And you can see for each area of law, we had as little as 1 instance. And a few hundred instances for each area of law. And so what we have here is a small data problem. We don't have a lot of information to learn from. And so as a solution to this small data problem, we leverage information from what we call pre-trained models. And the pre-trained models that we used is called BERT, which Tim will talk about later. Now, BERT is trained on 800 million words of the book corpus by Google, and also 2,500 million words from 2,500 million words from English Wikipedia. And so BERT doesn't know anything about legal NLP or anything about our task, but what it does do, it gains us knowledge about language usage. And then what we can do then is we can guide the model or fine tune the model for our purposes. Okay. So once we have got our pre-trained model, and then we fine-tune our model with your annotations given the gold standard data set. Once we've built the model, we want to know, we want to have a way to measure how well the model performs. And so we have these 3 metrics called precision, recall, and F1 score. So precision is a metric that tells us that when a model labels something as a particular label, it it tells us how often we get that right. So all of these measures are between zero metrics, are all between 0 and 1. And for precision, the closer we are to 1, the more precise the system is. For recall, that's a measure of missed opportunity. So the higher the missed opportunity, the lower the number is. That means the closer it is to 0. And so what precision looks at is, I think it's what it looks at all of the instances where the model says, yes, this is label X, and it is true that this is label X. So this is what we call, these are all of the instances where the model has labeled something positively as label X. So if it's correct, we call this a true positive. But if the model labels something and then it's wrong, we call this a false positive. So precision looks at the the proportion between true positives and false positives, whereas recall looks at missed opportunities. That means we said, oh, this is actually not, this is not X, this is not the area of law that you are looking for. This is not the area of law that you are looking for. And so we call this a false negative. And if an F1 score is a way for us to measure the overall performance of a model. And it's a combination between precision and recall. Okay, so, this is how our system performs. So what we did was we developed 2 baselines just to make sure that that we could outperform basic heuristics, so that we knew that our model was actually doing something, something good and something worthwhile. And the 2 baselines that we had developed were random and most common. Now, random just basically randomly chose any area of law of the 33 that you could have chosen from in the tag game. And most common is basically of all the documents that you did see, it chose the most common areas of law that you labeled each document as. And so the most common labels were litigation and dispute resolution and employees and volunteers. So if we just decided to just label everything with litigation and dispute resolution and employees and volunteers, then our precision would be at about 25%. Now these 3 systems that we had built, they're called, I'll go from the bottom up, soft labels, ratings, and gold. So soft labels is a system that takes into consideration what all of the annotators had annotated each document as. But it looked at the proportion of annotators that labeled each area of law. Ratings took into consideration how you rated your certainty, how you rated the certainty that a particular area of law, a particular text should be labeled as a particular area of law. And gold is basically the majority class that I was talking to you about before. So here you can see that in terms of precision, the rating system performed the best at around about 84%. However, the system as a whole doesn't perform quite as well as soft labels because recall is quite low. So overall, our soft label system actually performs the best, even though it was only 78% precise. Okay, so actually So 78% is actually quite low. So if you think about it, that means for each label that the model emits, it gets about 1 in 5 wrong, and that's actually quite high. That doesn't seem like a really good result. But if we have a look back on our areas of law and the number of instances per area of law, we can actually understand why. So if you have a look at the line for environment here, there are only 7 instances that are labeled with this particular seven documents that are labeled with this area of law, which means we don't actually have a lot of information to learn from. So we would expect that whenever the model emitted environment, that perhaps we couldn't trust it, or perhaps it was wrong often. However, if we had a look at, say, employees and volunteers, we would expect, well, with about, 550 instances, that there was enough information for the model to learn from. And so what we decided to do was to break down our model, the output of our model, and into areas of law. So we decided to find out what the precision is. Well, actually, we did precision, recall, and F-score, but I'm just showing you here precision for each area of law. And what we did was we grouped them into tiers. Now, in tier 1, we had the areas of law that we believed could be trusted if the model did emit this this particular label. Then we know that that it can be trusted. So, for example, for our test set, there were 73 that the model had labeled as migration, and 70 of those it had got right. For employees and volunteers, there were 538 in the test set that that the model had labeled as employees and volunteers, and it got 501 correct. And so we had 4 tiers. This is tier 1, tier 2, and then we've also got tier 3 and tier 4, which were quite lower down in precision, which I didn't have enough room to show you here. But I just wanted to show you that for the areas of law, for certain areas of law, that, that the model does perform well and it can be trusted. Okay, so we wanted to do some further analysis now with Justice Connect's intake tool. People who are requesting help could self-identify as, particular groups if they chose to. And so we got these labels and we wanted to see whether across the board for all the groups, if the model performed in a uniform way. And you can see here that for Aboriginal and Torres Strait Islanders and for seniors, the model did not perform quite as well for documents that are written by those groups. And so we thought that, so what I'll do is I'll concentrate more on seniors here because that was the model performed the worst for them. So what we had thought was that perhaps when it came to seniors, it may have been that when they were creating requests or when they were asking for help, maybe they were asking for help in certain areas where the system was going to perform badly anyway. And that's the reason why the model doesn't perform well for seniors. However, when we did our analysis, we could see that many of the areas of law that they made requests under actually fell under tier 1 and tier 2. And so that hypothesis was dashed. And so we also thought that maybe that for all the groups that perhaps the seniors, the number of seniors documents was too small, that we couldn't have possibly learned anything about them. However, you can see here that there were a total of 102 seniors documents, and also 91 and for people who lived in public housing, and 104 for LGBTQI, which is comparable to the number of documents for seniors. So here, it seemed that through our analysis, we had discovered this bias in the model. And so we asked ourselves, what can we do to address this bias in the model? So Tim is going to talk to you a little bit about this.
Thank you, Mel, and thank you, Braden, as well, for doing such an excellent job of contextualising the project. And I should just mention the third member of the Melbourne Uni team, Jehan, who was on Braden's introductory slide, is in and out a little bit. Unfortunately, got pinged as having visited a tier 2 exposure site and has rushed off with his family to get tested. So yay, contact tracing, but poor old Jehan. So he's on the lines on and off and can potentially answer questions, but will not be doing any presentation. Okay, so let me just share my slides. Okay, so we ended up with the cliffhanger from Mel about observing that we had disparities across different demographics within the data. And the question then is, where do we go from here? And obviously in the context of Justice Connect and the, I guess, type of client that Justice Connect is dealing with, and the social manifesto, if it's appropriate to put it that way, in terms of the values of the organization. Obviously, that's not something that we can live with. We need to make sure that our models are performing equally well for different classes of user. Let me just step back for a sec before I talk about fairness, just to talk about BERT. So Mel mentioned we're using BERT, this pre-trained language model, as the basis for our models. It's worth understanding a little bit about how BERT has been trained to understand where this has come from in part. And this is actually a recap of the presentation that I gave in December of last year for those who are in attendance there. So apologies if you've seen these slides before, but I figured there may be some people on the call who weren't part of that. And possibly I was being too technical in that presentation anyway. So those of you who were, you can have a second go at it. So, I'm not going to dive into all of the technical details. I just want to sort of give you the very superficial run through of BERT, just to give you a feel for how the model is built and why then there will be implications in terms of downstream fairness when we use the model in different applications. So the way BERT is structured is you have your input. So in this instance, we actually have two separate sentences. My dog is cute. And then the second sentence, he likes playing, and playing has been separated into two separate tokens. That's not super important for what we're discussing. The first thing that BERT does is map each of those tokens into what's called a token embedding. All we mean by embedding is a vector, a big list of fixed dimensionality, so fixed size of numbers. Okay, so whenever I say embeddings, just think list of numbers. So we've basically got a dictionary where we've got a token embedding. We map each of these words onto this big list of numbers. We then separately have what's called a segment embedding, and the purpose of that is simply to expose the structure in the input. So in this particular case, as we said, is made up of two separate sentences, sentence A and sentence B. So the job of the segment embeddings is to capture that fact. The fact that these first, whatever it is, 7 tokens are part of the first input and the remainder of the tokens are part of the second input. Okay, so if it were all a single sentence, they would all be EA. If it's two, we've got EA and EB, and we can have as many different parts to it, which we can index separately using these segment embeddings. But how these represented, again, it's just a big list of numbers. And then we have position embeddings as the third part, which is simply a way of representing where each of these words occurs or tokens occurs in the input. So the fact that dog, for example, is the 0, 1 second, as in third, but because we're counting from 0, token along. And that just gives the model a way of capturing where, relatively speaking, in the input this particular token occurred. Okay, so that's sort of the very basics. Then what we have is something called attention, which sort of learns, and you actually have multiple layers of attention, weights relative to particular tokens or particular classification tasks over the different layers in our model, so over these different lists of numbers, to try to learn, well, what's the best context that I can use in terms of weighting these different things to perform this particular task, which comes to the pre-training stage of this. Where do these numbers come from in the first place, which I'll talk about in a couple of slides. But assuming we've pre-trained our model, in terms of actually performing something like a classification task, which is what we're doing in the Justice Connect scenario, we take the input, we feed it through multiple of these layers. So for the basic model that we're using, it's 12 of these layers all stacked one on top of the other. And then out of the final layer, we take the first token. So the first token is sort of trying to be a capture of the overall semantics, the overall content of the input. And we predict on the basis of the big long list of numbers that is represented in that embedding, the area of law or different areas of law, say. And if it's multiple sentences or documents or whatever's we have in our input, then we'll largely do the same thing in terms of the output. We'll just represent the structure via this the second layer that we talked about before. But anyway, that's not relevant today. So pre-training, what is a pre-trained language model and where do these numbers come from? We use this trick called self-supervision. And all that means is Mel mentioned English Wikipedia and the books corpus. So basically we take lots and lots and lots of textual data, and we're going to perform two very basic tasks over that data. The first is a masked language model task, where we're simply saying, out of a particular input, whether it's a sentence or something else, we're going to pretend that we don't know what words appeared in particular locations. So it could be one or more words, which we're masking out. So masking in the sense of covering over them and asking the model to reproduce those words. And that's the classification problem that we're performing. So we know what the word was because it was there to begin with. We just masked it out so that we can do self-supervision in the sense that we don't need to have any painstaking manual labeling of data. We can construct as much what we call training data as we want simply by masking different words out randomly from different inputs at massive scale and just repeating that over and over and over again. Billions and trillions of times until the model gets better and better at predicting what word is missing. And in some contexts, it's going to be an easier task than others, but hopefully in aggregate, it will get better at doing that task. So that's the main component of it. There's actually a second component where you have two sentences and you try to predict which one came first. So you randomly mix up the order of the two and get the model to predict, well, in the original document, did the first come first or did the second one come first? And again, you just do this over and over and over again. You can generate as much data as you want because you're simply taking the raw data and turning that into a classification task. And that's the basis of this pre-training that we're talking about. Okay, then you do the fine-tuning in terms of actually trying to perform the classification task in terms of the areas of law, in our case with Justice Connect. Okay, and this was simply the point that it worked very, very well, better than what anyone had achieved up until that point. So it's a very powerful tool. So hence this has kind of taken over. I might just skip over this. This was from the original presentation. It's not super important. They're big, they're very computationally expensive to train, but surprisingly effective, and lots of parameters, as in billions of parameters. They're very big things. Okay, so that was an aside talking about pre-training and what a pre-trained language model is, and we'll come back to talk about that later. So fairness in AI. So let's just think more broadly in the first instance. Where is this an issue? Why is it an issue? So I just want to talk about a couple of topical examples, some very recent, just to sort of make the point of how pervasive a problem it is. You know, it's very much the not the dark underbelly necessarily of AI, but something that there's increasing awareness of, and it's a very real world issue when you deploy models in the wild. So one very recent one from earlier this week, in fact, was Twitter. There were various reports earlier in the year about the auto cropping algorithm. So if you have an image, a larger image with multiple people in it, say, Twitter has an auto-cropping algorithm that will select a sub-image from amongst that, and usually pick out a face or a couple of faces, and that's what you'll see in your Twitter feed. What people had picked up on was the fact that it seemed to be biased towards particular types of face. And Twitter actually, to their credit, ran a kind of tell us how badly biased our algorithm is competition. You know, offered a bounty of $3,500 to the person who could best expose the issues with their algorithm to then act on it and improve it. And the results of that, the winner of this, which was announced earlier this week, was actually a PhD student from Switzerland, who showed that, you know, it was actually even worse than people had thought. So basically, people with lighter skin tone, younger, more effeminate, and, you know, with warmer tones, but, you know, basically young white female faces, or effeminate faces at least, were what tended to get selected as the auto cropping. So, you know, there's definitely a bias against particular skin tones and ages, and yes, not doing a good job. So that's one. In the legal domain, perhaps one that's closer to home, and I suspect people are aware of, is the now notorious Compass system. So it was a commercial risk assessment tool which predicted, or gave a probability prediction of recidivism in the next 2 years for an individual, and, you know, was used quite heavily for over 1 million cases in the US legal system, but shown to have quite severe biases, you know, based on gender and particularly race. And so things have moved on, thankfully, since then. Another much more recent one, which is very much happening as we speak, again in the US context, is a tool called Amazon Transcribe from AWS, Amazon Web Services, which, you know, as the name would suggest, it's a transcription tool. So takes speech and transcribes it into text, which has been deployed in a couple of state prison systems, including New York. And there's plans to sort of roll it out more generally and give people in correctional services the ability to monitor phone calls with inmates on the basis of the output of Amazon Transcribe, despite the fact that speech has been shown to have very severe disparities across different demographic groups. So, you know, there's all sorts of risks in terms of what might come out of the naive use of such a system in terms of downstream repercussions for inmates. And this is more of a personal one for me. So there's a task called language identification, which is simply, I've got to document what language, or predominantly what language is it written in. So the sort of thing that your Chrome web browser does if you open up a page in a language that you don't speak relative to your language settings, it will say, do you want me to translate this into a language that you do speak, into English, say? So, it's simply making the prediction of, is this an English document, or is this a Greek document, or is this a Swahili document, or whatever else? So this is an area that I've worked in for over a decade, I guess, and we have a very widely used tool, something called langid.py. And this was work not done by us, but by a group at Stanford a couple of years ago in 2017, to show that there was a very strong correlation. So we're the blue here, we're the worst. But everyone is bad to some degree. The accuracy across different varieties of English. So Australian English, say, versus US English, as much as there is a national variety of English, but anyway, using tweets from these different countries, and I'm trying to predict what language they're in, English or otherwise, and what's the recall, if you can remember what Mel was saying. So out of all the things that are in English, what proportion do you actually correctly predict? And did a correlation with the Human Development Index of the country that particular variety of English was spoken in. And what you find is this horrible, horrible correlation that for those countries which have a high Human Development Index, like Australia, say, the model does very well. For countries which have a much lower Human Development Index, like Nigeria, the model does very poorly, i.e. the model is basically a rich gets richer sort of a model. It does well for the haves in the world and does less well for the have-nots, which if you're trying to use this for perhaps health monitoring purposes, say, particularly in developing countries, then the performance you're going to observe is going to be much less than what you might observe in the context of your home country. So very much a confronting, for want of a better word, road to Damascus sort of a thing for me personally, in being told, this model, which tens of thousands of people throughout the world are using, it has all of these baked-in biases. Okay, so what do we do? What is fairness, perhaps more broadly? So in an NLP, so in terms of language, at least, people tend to talk about fairness in two guises, in terms of source fairness or source bias, and target fairness or target bias. So source is, where does this text come from? So based on the demographics of the author of the text, do we observe disparities in the accuracy of the models? Exactly the sort of thing that Mel was reporting about relative to the data that we got from the tag game. So for example, if I presented this text to you, prizes for guessing that this is Princess Bride, or the re-release of the remastered Princess Bride. But if
I think that we're on the wrong slide. I can only see the BERT slide.
Oh.
Yeah.
Oh dear. So you've been on the BERT slide the whole time?
Yeah.
Gosh. How odd. Let me stop sharing for a moment and try resharing. I'm not sure if it was just frozen or...
Maybe it was frozen.
Try again. Thank you for telling me that. Do you now see Amazon Transcribe?
Yes.
And if I go forward a slide, oops. Yeah.
There we go. Yeah, it's going forward. So what is fairness?
What is fairness? Okay.
Yes.
I'm not sure what happened there.
Yeah.
Okay. Anyway, let me know if there are any more glitches. Sorry about that. So the text, which you can hopefully now actually see, is an excerpt from a movie review, so from a prominent reviewer. So I'm not exposing any personal details here. It's from The Guardian, in fact. But you can probably guess if I ask you to name the binary gender of this individual and the age you'd expect them to be, I'm guessing that you would be able to make an educated guess that it's a male, and perhaps an older male, just based on the tone, the style of text, and you would be correct. So this is what source bias is about. So there's no explicit indication of the fact that this is a male or what their background is, or anything like that. You may even be able to predict what country they're from, but I guess I told you it was The Guardian, so that's an easier one. But implicit in the writing style and to some degree the content, I guess, you can guess as to the identity, and that's where bias starts creeping in. So the flip side of the coin is target bias. So this isn't what we're interested in primarily in the Justice Connect case, but it's language which is directed at particular demographics. So, a classic case from English would be gendered pronouns, say, and the point in this particular example isn't, we've only got mentions of females here, and apologies for the example, it's sourced from Wikipedia from one of the well-known data sets. The point here is we have an ambiguity. Is her Eliza Bryant or is her Polly Simmons? And the fairness creeps in here because what tends to happen is the pronoun resolution systems do better over male pronouns than female pronouns. So they'll tend to get the female pronouns wrong more often, even if it's, in this case, obviously it's a gendered pronoun. We know it's going to be a female, and it's just a question of working out the two. But if we substitute in male names, we will tend to do better for largely the same context. Okay, so when we talk about fairness, we tend to talk about private attributes or protected attributes. They can be all sorts of things. It very much depends on the particular scenario that we're working in as to what those are. And in the Justice Connect case, as Mel mentioned, things like seniors and Aboriginal and Torres Strait Islanders were two great examples of a private attribute. Other ones might be sexuality, which Mel also mentioned, age, say. So, and depending on the context, the relative sensitivity of these is going to vary, obviously. And so in different contexts, people look at this, and so it'll be different combinations of private attributes and different tasks. So in the hate speech case, it tends to be target fairness, people singling out particular demographics and saying horrible things about them, with the classic one being race. Pronoun resolution that we mentioned now, again, it tends to be target, and in the English case at least, based on binary gender. In terms of the author or source fairness, it tends to be things like reviews. So I can do a better job of predicting, is this a positive, or is it a 3-star or a 5-star or whatever review for particular demographics than others. So middle-aged males, particularly middle-aged white males, you're in, as sad as that is to say. And so the list goes on, even for things like syntactic analysis, trying to work out what's the underlying syntax of a given sentence. If it's written by a middle-aged white male, will tend to do a better job of it because the training data tends to be from newspapers from the 80s, say, which were very much written by journalists of that particular demographic. So there it's a bias that's baked into our data sets. Sorry, need to be slightly conscious of time. It's 4 o'clock. Let me go through this quick. Well, let me actually skip over this. So suffice to say, there are different definitions of fairness. The one that we're interested in is this notion of separation. So the relative performance should be the same across different demographic groups. I've prepared way too much material, as always. We may have to organise a follow-up one where I can sort of go through this in greater detail. Let's skip over evaluation. So how do we train fairer models? So you might think, surely the simplest way to do it is if we don't expose any demographic variables, even if it's target variables to our or source variables to our models, they're not going to learn these sorts of biases. So I'm using the example of, we've got these very cute little soft toys. So we're trying to predict things as either elephants and rhinoceroses to try to sort of diffuse some of the sensitivities in terms of some of the demographic groups that we tend to be looking at. So if I have information about the color, say, that shouldn't be relevant to the prediction of whether this new image is an elephant or a rhinoceros. So if I simply obfuscate that in the data, surely the model is going to not learn these sorts of biases. And as we've seen from Mel, that's not the case. If anything, the models tend to amplify the biases simply by sort of pretending that we don't know these attributes. And the reason for that are a multitude. So it's things like the pre-training data. So going back to what we were saying about BERT, it's been trained over lots of Wikipedia and book corpus data of a particular style. There's a very big disparity towards male editors, unfortunately, in Wikipedia. So you've got sort of source male and to a slightly lesser degree in the books corpus as well. It can be in the labels as well, which was something that Mel was talking about again. So imbalances in terms of the labels. Can also be imbalances in terms of the private attributes. So this is a question of representation. If we have certain demographics that are overrepresented, so this is exactly the case that we have with our 80s journalists. The model has seen a lot of text from 80s middle-aged white journalists, and so that's the sort of text that it's going to do well over in terms of syntactic analysis, say. And there's also an element of machine learning doing what it's supposed to do, as in based on the way that we tend to train them, as in do as well as you can in terms of accuracy. So if you are doing something like an image labeling task and you've got a scene with someone cooking, and you've got lots of examples in your training data of a woman cooking or a man cooking or whatever it is, and you're not sure, the model isn't confident about whether to generate man or woman. If it's seen a lot more cooking scenes with women in them in the training data, the best thing for it to do in terms of maximizing accuracy is to generate woman. If in doubt, go with the bias that you know in the data. So in a way, the models are doing exactly what they're supposed to do, and exactly the job that we've trained them to do. So it's partly an intrinsic property of how we tend to train our models. So what can we do? So a sort of next step up from that is to say, well, if we know there are imbalances in terms of representation in the training data across our demographic variables, we can balance that artificially by downsampling, say. So if we've got, in this case, we've got whatever, twice the number of blue as we have purple soft toys. So we'll simply remove 2 of the blue, and we'll balance that up across our elephants versus rhinoceroses, say. This is being a rhinoceros. So if we just take those out of our training data, then everything's sort of balanced up. How does that work? The answer is it does work in terms of fairness to some degree, but what it tends to do is drive down the raw performance. So if we were doing badly for an underrepresented demographic originally, the overrepresented demographic, we're going to bring down performance for them, which, okay, it's a solution, but it means we're going to the lowest common denominator. We're sacrificing our performance. Ideally, what we'd like to do is bring up the accuracy for the underrepresented demographics, of course. So how can we do that? And I'll skim over the technical details, but intuitively, what we'd like to do is to have a model which is really good at predicting the target variable. So is something an elephant or is it a rhino? And as bad as possible at recovering the private attributes. So as part of the prediction of elephant, I want you to have no idea whether this is a purple or a blue or a gray or a whatever else elephant. And the form of representation that you're generating should not capture any of that information at all. And I want to explicitly train it so that that happens. Okay, and I'm going to use the information that I have about these private attributes in the training data to achieve that. So what does that look like? Hand waving vigorously, because there's a lot of technical detail here, but essentially what I want to do is say, so I'm predicting my area of law, say, or whether it's a rhino or an elephant in my example, but I'm also going to have separate predictors of, for each of my private variables, so our color in our toy example, what is the color? And the trick is to train each of these discriminators, these predictors of these private attributes, such that they do as badly as possible. So I want to do as good a job as possible of predicting rhino versus elephant, and as bad a job as possible of predicting color or whatever my private attribute happens to be. And the way I do that is I iteratively train my models. I train my classifier for my target variable first, and then I train my discriminative adversarial discriminators, and go through that a couple of times until everything hopefully balances out. And one issue, and let me finish up in 2 minutes. I do want to leave a bit of time for questions. Another issue that we have as part of this is, of course, what happens when we don't have full data in terms of our private attributes. So a nice thing about this adversarial method is because we've decoupled the training of our base classifier, the rhino versus elephant classifier, and the adversarial discriminators. That's fine if the data is slightly different in terms of training them in each case. There are lots of other methods that I could talk about but won't. So let me just wrap up. We talked about, Mel talked variously about the results in the Justice Connect context on the basis of the wonderful data that we got through the tag game. I then took over in terms of talking more generally about fairness and what is unfair AI with picture examples, introduce this idea of source versus target, and different ways of training models to be fairer, which is exactly the space that we're planning to head off into in the next little bit. And there's all sorts of activities and cool results suggesting that all is not lost. We can achieve this kind of holy grail of keeping performance up and bringing up the accuracy for the underrepresented groups. I will stop there.
Thanks, Tim. That was great. So we'll move over to some questions. Really appreciate how well that's been covered. I think if I didn't have a great sense of fairness before, I feel like I'm well and truly covered now. So appreciate that. Yeah, if anybody has any questions, either for Tim, Mal, myself, or Jehan, if he's present, welcome to pop them into the chat. I just want to thank everybody in attendance and just point out that we all appreciate the work and time that's gone into tagging and labeling and supporting us in doing this work. It's very much appreciated. The same goes obviously for Mel and Tim and Jehan. They've also enabled Justice Connect to really just do this project generally. So it's really appreciated. Yeah, if you want to drop some questions, go for it. Next steps for us, I'll just talk broadly while people kind of muster up their questions. The next steps for us is we'll be looking to integrate this model into our intake tool, and that is really just building an interface that we can allow our intake to communicate with in a way that we can pass the legal descriptions that our help seekers give us, and then we can bring back that result from the classifier and provide that to the user in a suggestive way that allows them to either disregard what the AI says or take that suggestion on board and proceed through the intake in an informed manner. Yeah, and then hopefully from there we can do a bit of open sourcing and hopefully make this more readily available to other legal assistance organizations or legal organizations generally that want to utilize this web interface to communicate with and get a sense of areas of law that pertain to their problems. Yes, any questions? Oops. I think that might be it. Any comments, Mel, Jehan, Tim?
We must have been really crystal clear then.
One way or the other, either bamboozled people, case apologies, or very, very clear. But yeah, no, it's a very, very exciting collaboration. Everything that Braden said about us, I would return back multifold. I mean, the data, I mean, the importance of the data, the importance of the services that Justice Connect is performing are phenomenal. But the value of the data that we're getting from the tag game is just incredible. There's so much richness to mine in terms of trying to boost the performance and just further improve efficiencies in terms of the intake tool.
And the one thing that we really liked about working with Justice Connect is that they have a great idea about what AI can and can't do, and so for us to talk to them about in depth about the different areas of law and where it performs well and where it doesn't perform well. Now, even though in some instances, like when we just give you the overall performance, you might think, oh gosh, well, 1 in 5 we get wrong. That's terrible. We're going to throw the baby out with the bathwater. But no, that's not the case. There are some instances where we know that we can still use the model that we have. We just have to know how to use it. And, cooperating in that way has been really great.
Yeah, that's so true. And it's also good to point out that it is an iterative process. Since the training and analysis has been done, we've collected almost double the amount of samples. So that'll go in retraining or further training the model to better hone in on those areas of law. And hopefully with support of Melbourne Uni, we'll be able to bring some of those numbers up that we've struggled with, and especially the demographics as Justice Connect starts to pivot towards helping those particularly affected cohorts. Cool. Well, I might call this to a close. Once again, thank you everybody for attending. It's been great having you join us along with this journey, and we look forward to having you on board for the rest of it. So thank you, Mel. Thank you, Tim, and thank you, Jehan.
Thanks, guys. Thank you.
Thanks all. Bye.